Okay, so my topic is about mapping and modeling of groundwater and resulting subsidence for London and Delhi. So groundwater extraction can cause land movement and which can cause major and recurrent harm to infrastructure and water storage capacity of aquifers. Both London and Delhi and both the capital cities of UK and India, it is London and Delhi, they are witnessing ever increasing population in last few decades, and this increased population is causing extra pressure on groundwater, and this extra pressure on groundwater can lead to land movement. Thus, modeling and mapping of this ground movement becomes very important. So we will discuss groundwater induced subsidence in both London and Delhi, and then a very short description of a mathematical model where we link groundwater subsidence and groundwater induced subsidence. So these are our London subsidence results. So we have used 99 Sentinel-1 images and we have processed these images using NV Sarscape, and the principle we have used is persistent scatterer in SAR, so PS in SAR. So we can see overall for London, the land subsidence is stable. We are not getting any alarming or very critical land subsidence, but we can see some local patches of land subsidence as well as uplift, which I've shown by blue brackets here. And the overall mean rate of deformation was negative, that is 0.08 mm per year. So we will not discuss all the cases, just two cases we'll discuss for London and similarly for Delhi. Again, this is for Delhi. We have used Sentinel-1 images, 95 images processed using NV Sarscape and PSNSAR to compare so that the two results are comparable. In conjunction, we have tried to keep most parameters similar except for some local geological parameters. And we have found that mean rate of deformation here was also negative, which shows that land is going down. But again, by and large, it's not, by and large, it's stable, but some few areas have shown very critical land subsidence, and we will try to read them in details. So for example, here in the West, we can see very dominant uplift, very dominant subsidence, and here also very dominant subsidence. So these two as a case study we'll read. So first case study which we like to discuss is in London, that is Northern Line extension. So in this case, we see for Battersea Power Station to Cannington Station, we see a clear differential land movement. So this red indicates subsidence and blue area here indicates uplift. Very interestingly, groundwater change on the same time period, which is can be seen. So these groundwater maps were obtained from observed groundwater data, which was provided by the which is government agencies, and this is our subsidence result. So we could see that subsidence and groundwater are directly correlated. For example, in this Cannington area, we can see the blue area represents uplift. But when we draw the time series of this, then we see that initial part of this is showing subsidence and then suddenly uplift. And when we see the literature, then for this northern line extension, tunneling was done in this area, in the Cunnington area, which started in 2016, end of 16, and stopped by 2017 end. So groundwater was taken away, was extracted for this groundwater extraction. And once the groundwater extraction was stopped and the construction was over by beginning of 2018, then the groundwater was released back, and due to groundwater recharge, we could see a heave and we could see continuous land going up. So clearly this particular land subsidence here in this area is dominated by groundwater change. And for the Battersea area, continuous groundwater extraction is taking place, as we can see from the groundwater map as well. And then this is subsidence time series going down. Overall, if we travel from A to A dash, that is from That is the path of our Northern Line extension in London. So if you travel from this, we see a differential land movement where initially nearby the Battersea area, it's subsidence, it's negative. You can see below zero, and then when it goes reaches near Kennington area, we can see some uplift. These are some observations, mathematical units. So we can see that for the blue area, that is L1B, our average mean rate of deformation is uh, positive, and here it is negative. Okay, so this is a brief discussion where we are able to map direct correlation between groundwater and subsidence. Of course, there are many other factors which can affect land subsidence, but some factors are dominant in some areas, and we are only interested in this study about groundwater and how this groundwater can cause subsidence. So similar pattern can we have been able to map in Delhi, where this is a magenta blue line metro construction. So if we see this area D1B, so this area we can see is sandwiched between blue line metro, and this blue line metro was constructed in 2006, but the magenta line is passing from this area. This magenta metro line was constructed in 2016. So it started from 2014 and finished in 2016. Once the underground construction was done, again the groundwater was released similar to our Kennington area. And due to this release of groundwater, this heave can be seen and we can see a clear uplift. This area, on the other hand, D1A, where we can see clear subsidence, this is because this is a very heavily populated area, dense population, and there are a number of groundwater wells which are extracting groundwater. Due to this extraction and overuse and less discharge, we can see a subsidence here. So this is for subsidence, a similar groundwater pattern again. The groundwater map has been created by observed groundwater data provided by Indian groundwater agencies and interpolated on IDW maps. So again, what we're trying to show here is how subsidence can be directly correlated to groundwater. Till day, we know by and large that if there is an extraction of groundwater, then the land will go down. If there is a discharge of groundwater, then land will go up. But a clear example in two different cities in two different corners of the world, London and Delhi are geologically and geographically are very different, but when subjected to same engineering purposes, underground construction or groundwater removal, we see the response to groundwater removal in terms of subsidence is similar. So this can be a phenomenon which may be a global, and we can our study when this is under review now in a major publication house, and once it will be published, and then I'm sure that this will gain interest from other researchers and in other parts of the world. So that was about differential movement nearby. This is another example which we have been able to map, which is showing clear subsidence due to direct groundwater withdrawal. And this is in Wimbledon area in London. So Wimbledon area in London is well known. It's again a very highly populated area. It has got number of roads, buildings, structures of importance. So groundwater requirement is very high in this area. The groundwater map suggests that a lot of groundwater is extracted and less is recharged. There also, this area is very close to the Wimbledon fault. So fault also plays its role in defining the subsidence pattern. We can see the time series of the subsidence pattern is showing that it's going continuously down, right? So in this area we can see a green small triangle. This triangle shows the location of Martin Abbey public water supply well. This is one of the most highly used well in London, or we can say it's uncontrolled extraction. So we have a lot of literature where it says that the groundwater extraction from Martin Abbey well is uncontrolled, and this uncontrolled extraction kind of creates drawdown in the whole area, nearby area, and this is what is the main reason for subsidence here, uh, and and can be seen clearly in our maps. So a similar study, a similar area in we have been able to find out in Delhi, where this is the region, the blue, excuse me, sorry, the blue line here is the Delhi Haryana border. So these are two states and the border. So the area which we have marked as D2B, this area is highly populated, again, densely populated, because it lies in the outskirts of Delhi. So the people living here did not need to pay doesn't need to pay heavy expenses of living in capital city, but they can use most of the resources of capital city. So that's why a lot of population these days is getting concentrated, especially in the last decade in this area. So this population again is creating a lot of again pressure on groundwater, and this groundwater extraction is causing our subsidence pattern here, which is again can be clearly seen by our time series as well. Similarly for D2A and D2C, if you see D2C, then there is more subsidence, but groundwater extraction is not so high here. So this could be another reason, maybe less recharge of due to rainfall or some fault or some nearby. Or there is also an interesting fact is that if you see this blue line, it's a metro line construction for Delhi airport, that is Indira Gandhi International Airport. So when this metro line is constructed, it's still under construction. So a lot of groundwater is extracted to make this underground metro construction. This could also play important role in this. So there could be various factors, but the most important factor dominating here is again Delhi and Haryana in the is groundwater extraction. So the first in Delhi, which we have first map which we have seen for Delhi. So this is comparison of we try to see how these groundwater before monsoon, monsoon and post monsoon in India can affect this, because monsoon is major critical parameter, rainfall is major critical parameter for the charge of groundwater. So we could see that especially in the later half of the year of our in the later half of our observation period, that is 2018-19, you could see that especially in this area, the when the increase in groundwater is taking place, and we could clearly see the land uplift is there, right? And when there is in especially on the left hand side where there is subsidence, which we said was due to high concentration of population, we could also see that groundwater is less in this area, and which is causing subsidence. And on the right, this is just showing spatio-temporal variation of subsidence for this area. And we see as we have just started our observation period in monsoon 1920, by the time we reach here, this area is showing major dip. So this was the initial period, greenish, where it's almost zero subsidence and uplift. This is relative, of course. And as we reach towards the end of 2019, we see here a strong uplift here and a strong subsidence here, which is of course not good. So this was all qualitative qualitative analysis of this. This created a need of a model where we could find a mathematical relation between subsidence and groundwater. So we have been able to develop from using literature a simple 1D mathematical model. So the model is again now under a review for publication. So I am not able to discuss all the equations and details, but the model is based on effective stress principle proposed by Tazagi, and it is using, we have used all the physical parameters like compressibility, porosity, void ratio, and what we could found is when we have given input as groundwater changes the input, and then the modeled groundwater, and then the modeled motion, that is the modeled land subsidence, and this is the Pearson model motion, and we could obtain a very good correlation with R square of 0.881. So this is just a, initial idea of the model, 1D model. We are working on it. Our team is working on it, and we will definitely try to build this in 2D and 3D as well. So thank you. This is all I have to share, and I'm open for questions. Please to ask any questions if you have. Thank you.